So in complex analysis, most important theorem, so that is necessary condition for the function f of z to be analytic. Okay, so this is necessary condition. So first we have to know what is an analytic function. A function f of z is said to be an analytic at the given point z equals to a or z naught. It should be differentiable or derivable at that point, okay, or in the neighborhood point. Statement: a necessary condition that f of z is equals to u of xy plus I into v of xy to be analytic in the domain D is that the first order derivative of u and v with respect to x and y must exist and must satisfy the equation dou u by dou x equals to dou v by dou y and dou u by dou y is equals to minus of dou v by dou x, or ux equals to vy and uy is equals to minus of vx. Here the given function is f of z is equals to u of xy plus I into v of xy. From that we have to prove this CR equation. So these equations are called CR equations. So that is Cauchy-Riemann equation. So according to here the given that, so this function f of z is an analytic, means we have to consider the according to definition, so that is a derivable means, so we have to consider the definition of differentiability. That is, for a complex number z is equals to x plus of iy of the analytic function f dash of z is equals to limit of f of z plus delta z minus f of z divided by delta z. As delta z tends to 0, it must exist and unique. So this is the definition of differentiability or derivability. So in this equation we have to substitute the value of f of z, so that is the given function delta z and f of z plus sub delta z. F of z means, so this is the given function, that is u of xy plus I into v of xy. F of z is this, f of z plus delta z means that is u of x plus sub delta x, y plus sub delta y, plus I into x plus sub delta x plus y into delta y. Then delta z is equals to x plus of iy as a complex number. Delta z means delta x plus of I into delta y. So these three values we have to substitute so in this equation. Therefore f dash of z is equals to limit as delta z tends to 0 u of, substitute these equations, okay, f of z plus of delta z minus of f of z divided by delta x plus of I into delta y. So in a complex number, real and imaginary parts are there. So two conditions we have to consider. First condition, suppose that delta z be a real part. If it is real means imaginary part should be 0. If it is an imaginary means then real part should be 0. So first case we have to consider delta z be a real number. So we have to consider delta y is equals to 0. Delta y is equals to 0 means delta z is equals to delta x, because it's a real part we are considering, okay. So wherever delta y is there, so in this equation that we have to put as 0, okay. So by substituting 0, so we will get this equation as delta z is equals to delta y, delta z is equals to delta y tends to, sorry, delta z is equals to delta x tends to 0, okay. So and here we have to separate the real and imaginary part. So u of x plus of delta x comma y minus of u of xy. So it is a real part divided by delta x as delta x tends to 0. Next, plus of, that is imaginary part, I into, that is v of x plus of delta x comma y minus of v of xy. This is imaginary part, I taking as common factor, divided by delta x as delta x tends to 0. According to definition of differentiability, so this is the function u with respect to x, that can be written as f dash of z is equals to dou u by dou x plus of I into dou v by dou x. So call it as equation number 1, okay. So in the case 2 we have to assume that let delta z be an imaginary. First we are considering as it's a real, so hence imaginary should be 0. Here we are considering it is an imaginary, then real part should be 0. Delta x is equals to 0 and delta z be, that is imaginary, delta y, okay. So that delta z should tends to delta y tends to 0 wherever delta x is there. So in this equation that we have to put it as 0 and write this equation. And here again we have to separating real and imaginary part. So this is a real part, this, and minus of u of xy divided by I into delta y. Next, plus of imaginary part I into that v of x comma y plus of delta y minus of this I is common and v of xy divided by I into delta y. I get cancel, and here it is 1 divided by I into, according to definition of differentiability, dou u by dou y, and here it is dou v by dou y. This 1 by I can be written as minus I, because 1 by I into I by I, in the numerator and denominator we are multiplying by the same term, so it becomes I divided by I square means minus 1, so it becomes minus of I. Therefore 1 by I can be written as minus of I into dou u by dou y plus of dou v by dou y. Call it as equation number 2. So here, by considering delta z be a real part, so we get the equation number 1. Delta z be real means imaginary part is 0, and in the case 2, delta z be imaginary means its real part should be 0, so we get the equation number 2. So since f dash of z is unique, and the equations, by comparing the equations 1 and 2, equating the equations 1 and 2, because on LHS part both are equals to f dash of z only. Okay, so therefore f dash of z means, so we are equating the RHS part. So, and again we are by comparing the real and imaginary part, dou u by dou x and dou v by dou y, and this imaginary part dou v by dou x is equals to minus of dou u by dou y. Okay,